solving equations is a very broad topic, but there are a few principles that apply for all solving of equations. What you're doing is you're trying to undo operations that are being done to the variable that you're trying to solve. So if you have a simple linear equation, again, a linear equation means that any variable is raised only to the first power. So notice my only variable here is x, and it is raised to the first power. That makes it linear. And if you graph this, it would be straight. It would not have any curve in it. So I'm trying to get x by itself, so I need to undo the arithmetic that's being done to it. Start from the outside in. You're actually going to do the order of operations in reverse. So the PEMDAS, or the please excuse my dear Aunt Sally steps, you're going to do those in reverse. So you're actually going to worry about the adding and subtracting first. So I want to subtract 8 from both sides, and that will give me just 10x on this side. And 54 minus 8 is 46. And if I then want to undo multiplying, I'm going to divide, and dividing both sides by 10 gives me x equals 4.6. You should check your equations by plugging the value back in. If I did so here, it's fairly clean to do so. And so 10 times 4.6 is 46, and 46 plus 8 is 54. Check, I did it correctly. Okay, so my solution is just the one number, 4.6, and I checked that it works out. I could have a slightly more complicated linear equation, but this is still a linear equation because the variable is to the first power. Here, again, you're going to do the order of operations in reverse. So you're technically adding 19. So I want to subtract 19 from both sides. And when I subtract 19 from the left side, I get negative 2/3 times x. And subtracting 19 from the right side gives me negative 12. Again, I could multiply by the reciprocal of my fraction, but I think I'll break it up just to kind of, show what we're doing actually when we do multiply by the reciprocal. You're multiplying by 3 to cancel division by 3. So whatever I do to one side, I have to do the same thing to the other side. So 3 times negative 12 will give me negative 2x equals negative 36. And if I divide both sides by negative 2, I will get positive 18 as my solution. Okay, so checking my answer, if I go back to the original and I put the number 18 in for the x, I will get 19 minus, now 3 goes into 18 6 times, so 2 times 6 would be 12, and 19 minus 12 is 7. So my answer checks. So once again, I only have one solution, and it is 18, and I have checked it. Looking at some other kinds of situations you might have, here I have again a linear equation. Now my variable is showing up in a couple of different places, but notice it's to the first power, so it's linear. Now in this case, I can't just start undoing the order of operations because my variable is trapped inside these parentheses. Now notice that there's a power of 1 technically here. When you have a power of 1, and only when you have a power of 1, can you distribute over adding and subtracting. So if I take 0.15 and I distribute across this difference, then I get 0.15 times 400 is 60. and 0.15 times 0.10 is 0.015, and that is the new coefficient on that x. So now that I did that, I want to look and say, oh, you know what? This is an x term and this is an x term. I can put those two together. So if you combine those two like terms, we get 0.805x plus 60 equals 1992. And then I'm trying to solve for x. So now it becomes undoing order of operations. So I'm going to subtract 60. When I subtract 60 from this side, the 60 is not being added anymore. And when I subtract 60 from this side, I get 1932. And then x is that divided by 0.805. And this is not going to necessarily be a clean number, but that's okay. Oh, I actually get 2400. I get a nice clean number. But just because your answer is not a clean number doesn't mean you've done something wrong. I mean, you do want to check your answer. In this case, checking my answer, it might be, you know, it's okay if you're kind of in a hurry to check with your calculator. So we're putting 2400 in for the x. And when you're checking, go back to the original equation, because you could have made a mistake from the very beginning. And there I go. I plug in the 2400 and I actually get the 1992 that I was supposed to get on the right hand side. So all looks good. So once again, there's only one solution and it's 2400. Looking at this example, again, I can't just start undoing order of operations. My variable shows up in a couple of different places. I do want to collect like terms. So the 4 is a number, the 20 is a number, a set number. So let's collect like terms by subtracting 4 from both sides. And the 4 then is undone on this side, and I get 16 over here. And then 12 divided by x is like 3 divided by x. They are like terms. They have the same variable term. So what I want to do then is add 12 divided by x to both sides, because if I add 12 divided by x, it is undone by that minus 12 divided by x. And on this side then I get 15 divided by x because I have like denominators. So when you have like denominators, you add the numerators and put it over the like denominator. And now I'm trying to solve for x, so x is in a denominator. Why don't we multiply both sides of the equation by that x? And so then I get 16x equals 15. And so then x is equal to 15 divided by 16. And there is my solution. Again, if you wanted to check your answer, we have 20 minus 12 divided by 15 divided by 16. And that gives me a value of 7.2. If on the right side I then take 4 plus 3 divided by 15 divided by 16, look, I get 7.2 again. So that means the left side equals the right side when I plug in my 15/16. So we solved that one correctly also. Here we have a couple more linear equations. What I would do with this one, I mean, yes, I could add 1/3 to both sides. That would be perfectly fine. I then would have to just reason out the arithmetic, you know, what is 4 plus 1/3. Instead, what you might want to do is multiply by 12, 12 being the common denominator, and then you'll have an equation that doesn't have fractions in it anymore. So if I multiply all the terms by 12. So I can't, you're multiplying both sides of the equation by the 12. So that means everything on the right side and everything on the left side gets multiplied by the 12. So 4 divides evenly into 12, and that term turns into 15 times x. 3 divides evenly into 12, and that term equals 4. And 12 times 4 is 48. And then 15 times x will equal 48 plus 4. Again, I'm adding 4 to undo the subtracting 4. And 48 plus 4 is 52. And so x then is 52 divided by 15. Again, not a nice number, but that's okay. You don't have to get a clean, integer all the time. If you're wanting to check your answer, again, just be careful. I mean, you could, do the arithmetic by hand too. I'm just trying to make our video not as long as it needs to be. Okay, so 5 times my answer, I think, is 52 over 15, and then that's divided by 4, and then subtract 1/3, and yay, we get 4. So we did all the steps correctly. We found the correct solution. All right, now here, again, I've got the variable on both sides, and I want to collect all the like terms, but before I could do that, I need to free the x from the parentheses by distributing. Again, it's legal to do that because my power here is technically 1. If you had a square, I would not be able to just multiply that 7 through. So I get 7x minus 56 equals 5x plus 8. And I'm collecting like terms, so I'm going to subtract 5x from both sides. And that gives me 2x minus 56 equals 8. And then if I add 56 to both sides, 8 plus 56 is 64. And so then x will be 64 divided by 2, or 32. So again, I'm dividing by 2 to undo the multiplying by 2. So it looks like I have a solution. All right, well, this is an interesting little case. I have a linear equation somewhat, except that it's actually a rational equation because I have a polynomial divided by a polynomial. But if I multiply both sides by the denominator, so if I multiply both sides by 4x minus 2 and both sides by 2, then on this side I will get 2 times 9x plus 3, and on this side I will get 3 times 4x minus 2. So again, when this side got multiplied by the 4x minus 2, it was divided by the 4x minus 2 in the denominator, and when this side got multiplied by the 2, that 2 got divided by the 2 in the denominator, and I'm left with then this numerator times that denominator equals this numerator times that denominator. They call that cross multiplying. All right, so now I truly do have a linear equation. And once again, I can distribute because the power is 1 here. If there was a power there, I would not be able to just multiply that 2 through. So I get 18x plus 6 on the one side, and I get 12x minus 6 on the other side. And if I then subtract 6 from both sides, I also could have added 6 to both sides. It's just I need to try to get variables on one side and numbers on the other side. So I get 18x equals 12x minus 12, and now I'm going to subtract 12x because I will eliminate the x terms on that side. Now 18x minus 12x is 6 times x. And on this side, the 12x is gone because of the subtraction. So I get 6x equals negative 12, and undoing multiplying by dividing, I'm going to divide by 6, and I get negative 2. So my solution is negative 2. Now if I want to check my answer, I can go back to the original equation, and 9 times negative 2, again, don't forget the negative, it will make a difference. And then 4 times negative 2 minus 2. 9 times negative 2 is negative 18, and negative 18 plus 3 would be negative 15. And 4 times negative 2 is negative 8, and negative 8 minus 2 is negative 10. A negative divided by a negative will be positive, and 5 goes into my numerator, and 5 goes into my denominator, and I get 3/2. So yay, we did it correctly. We checked our answer. So I have one solution, and it is negative 2. Now here, again, it looks like we have a linear equation, and that x is raised to the first power, but it's really not a linear equation because the x values or the x variables in the denominator, making it a rational equation. So I'm technically dividing a polynomial by a polynomial, making it a rational equation. But we can, try to get somewhere with it, and it might turn into a linear equation. If I multiply all of the terms by the common denominator, so x times x minus 5 will be my common denominator. And when all of the terms are multiplied, notice on this side I will get 1 times x minus 5, and the whole reason why we're multiplying by the common denominator is to divide out the denominators. So this turns into 2 times x minus 5, and the x minus 5's divide out here. And on this side, I get x squared minus 5x. So I no longer have linear because x is being squared. It's now a quadratic. But let's see what happens. 2 times x. Again, I'm able to distribute because I technically have a power of 1 there. If there was not a power of 1, I would not be able to do that. Alright, so we definitely need to collect some like terms. On this side I have 6x minus 10, and I have a negative 5x term on the right hand side. So I'm going to subtract 6x from both sides, and I will get negative 10 equals x squared minus 11x. Now the x squared is making this equation now not a linear equation. I will have to use strategies for a quadratic. So when you're trying to solve a quadratic equation, either by factoring or by the quadratic formula, I mean, unless it's just simply, x squared equals something, then you could, just busily undo the square. But if you're going to factor or use quadratic formula, you have to have one side set equal to 0, because the logic behind factoring doesn't work unless it's set equal to 0, and the quadratic formula is assuming that you've set it equal to 0. So I set it equal to 0 here. I'm going to factor because this is actually a fairly factorable quadratic. Notice x times x will give me x squared, and I have positive 10 as the back term, so these factors will both have the same sign, and I want factors that multiply to give me 10 but add to give me 11. I know adding because the factors will have the same sign. So negative 1 and negative 10 work in that case. X times x is x squared, x times negative 10, and then minus 1 times x, the minus 1 and the minus 10 add up to negative 11. And then negative 1 times negative 10 is positive 10. So this time I actually have two solutions. I have 1 and I have 10. If x is 1, this factor will become 0, and it times whatever this is will be 0. If x is 10, then this factor is 0, and 9 times 0 will still be 0. So I actually get two solutions in this case. And so if I went back to my original equation and I wanted to check my answer, you'd want to check both of those. So 2 over 1 plus 4 over 1 minus 5 would equal 2 minus 1, because 1 minus 5 is negative 4, and 4 divided by negative 4 would be negative 1, and that equals 1. So check. And then if I plug 10 in, because that was my other solution, 2 tenths plus 4 over 10 minus 5 is 5, and 2 tenths is 0.2, and 4 fifths is 0.8, and 0.2 plus 0.8 is 1. So both of my answers check. And so again, the solutions were 1 and 10. Practicing that same idea, here's another example. And this one looks worse, but it's really not worse. You're just gonna focus on the same idea. Remember, ideas in math don't change. You just, sometimes have to apply it to things that are messier or not as messy. So I'm going to multiply both sides by the common denominator. And so my common denominator actually is x minus 2 times x plus 3, because this factors to be x minus 2 times x plus 3. Notice x times x is x squared, and then 3x minus 2x is 1x, and negative 2 times 3 is negative 6. So this denominator is the product of those two. So multiplying both sides by that common denominator, and I'm kind of running out of room on my paper, so I'm just going to put 4, because if I multiplied this side by the common denominator, it'll divide out that entire denominator and I will be left with 4. Now over here, the x minus 2's divide out, the x plus 3's divide out, and so I get x plus 3 times x minus 2 equals 4, and then x plus 3 plus 3x minus 6 equals 4, and then 4x minus 3 equals 4, and then 4x, I want to add 3, and so that gives me 4 times x equals 7, and so x will be 7 divided by 4. So I know this one looked kind of messy, but when you actually multiplied both sides, when you patiently multiplied both sides by the common denominator, it turned into a fairly clean, nice linear equation, and I got one solution. So the other one actually looked a little cleaner at the beginning, but it gave me a quadratic, which was, slightly messy. We had to think about factoring then. And checking our answer, 7/4 is 1 3/4, so this one might be a good one to again review checking on the calculator. So 1 divided by, again, 7/4 is 1 3/4, so 1.75 minus 2 plus 3 divided by 1.75 plus 3. And that's the left side, and I get this messy negative 3.36842. And then on the right hand side, if I plug in 1.75 squared plus 1.75 minus 6. Yay! Look, I get that same messy negative 3.368. So we solved the equation correctly. We got the left side equal to the right side. Alright, so that was a nice little set of, various solving equations. Most of them ended up being linear. Again, this is just scratching the surface of solving equations, but all solving equations involve the idea of undoing the operations that are being done to your variable. So that's what you always want to focus on. Sometimes you have to collect like terms before you can actually just start undoing. Sometimes you have to distribute, etc. But when it comes down to it, you just try to start undoing all the operations until you get your variable all by itself.